Bonjour. You are in the Biostat and AI podcast with Darko and Bruno. And sometimes we talk about Biostat, sometimes we talk about AI, sometimes, like today, we talk about both together because Darko and I had a crazy idea. And instead of just trying to build it in our own, we're building in public so that you can help us tell us if we're geniuses or just stupid, or maybe you can take the idea and compete with us if it's such a good idea, or tell us not to waste our time. We think it's a genius idea. And what's the code name, Darko, for that new idea of ours?
Oh yes, the top secret code name for the idea is PoppyZ. Actually,
PoppyZ.
Bruno invented that. Actually, I have a cat which is called Poppy, and the cat was actually a guest in one of our previous podcasts. So Bruno got the idea. Hey, why don't we name it PoppyZ? After a cat. And my cat is really honored. Really honored. Thank you,
I'm
Bruno.
glad Poppy likes it. So let me try to define what PoppyZ, the new project we have, very ambitious, very exciting, is, and then we can ask you and Poppy what to elaborate on it. So the goal of PoppyZ, this new secret project that we're sharing with you exclusively today, is to use AI and pooled analysis and pseudo individual patient data, pseudo APD, which we have in our database called CLIN, to predict outcome survival curves. So the goal is to say, okay, in that clinical trial, there's a survival curve. We want to predict it without looking at it. And we want to use machine learning to predict that curve without having seen it. And the loss function to optimize, the goal of the machine learning is to be able to predict survival of standard of care, control curve, not the interventional curve. That's too hard, but the control arm curve. So in a way, it's one tack at synthetic control curve, isn't it? The famous big goal that so many people worked on, or the CITEL, the Medidata, the Flatiron synthetic control curve. That's what we're after. That elusive goal of having extremely good synthetic control curve so that you can avoid or reduce the reliance on control curves, on control groups. So that if I'm sick, I don't maybe need to be in the control curve, or maybe the control curve can be smaller, or maybe the trial can be smaller, right? So that's the idea, synthetic control curve. So explain for the audience a little bit the way PoppyZ would work. And just before you do that, if anybody is listening and has questions, please make a note on social media for us, and we'll do our best to answer your questions.
Yeah, I think this is really one of my favorite types of podcast, Bruno. And thank you so much for all the great all the great details that you shared. Before I actually start going into more details, I just want to share with our audience that me and Bruno, we sometimes have these brainstorms, and I always say, like, Bruno, no, this is such a genius idea, we should not ever share it with anyone, like it should be top secret. And Bruno is like, no, Darko, no, we should actually build in public. We can actually build. If someone can compete with us on this idea, they should. So Bruno is a very open mind, I would say. And that's, if everyone listening into this is surprised that we are sharing a very good idea with
Well,
public.
but I don't have the choice, Darko, because I'm a very creative person and I'm not
Yes.
a real scientist. So by definition, any genius idea I have, there's an 80% chance that is either not a good idea or impractical, right? But that's not, for a creative person, that's not bad, right? 20% of my ideas are great, 80% are not so good. So the faster we realize in which camp PoppyZ is, the less time we're going to waste.
That is just a incredible way of thinking. We're actually validating an idea in a way by using just sharing everything with everyone. And really, inspiring, Bruno. Anyway, going back to the PoppyZ that Bruno was mentioning, we LARVOL actually has a number of machine learning initiatives, AI and machine learning initiatives, and really some of them are actually pointed into predicting the curves. But this one, which was very interesting, actually relates to another project that we built previously with a fantastic researcher and a fantastic professional at LARVOL, um, who was actually managing that project, which is Judith Perez. And the product that we built was it's called actually the pooled Z. So we can leverage all the data that we have on Clean, and actually not only plot individual curves from trials. We can just take a lot of curves together and plot them together in this pooled analysis. So we can even create one pooled curve that comes from a lot of different trials. And so that's where the idea started for us. Like, if we have these machine learning initiatives and we also have the pooled Z, the ability to create pooled curves, that could effectively, if we combine those two ingredients together, that could be a very powerful product utilizing both machine learning and pooled analysis as a statistical approach.
Before you get into how we apply machine learning to our pooled solution, let me say something about the pooled solution that we built. So you and Judith and team, you built the largest cancer pseudo individual patient database, right? So you took all of these Kaplan-Meier curves, you digitize them, and then you apply some biostatistical method, the Guillot method or the Liu method, one of the two, I think the Liu method, maybe the new method, to take these curves and to extract essentially synthetic patients, right? So these are pseudo patients. They are digital twin of patient. They're not as good or as detailed as individual patient data, because the data we have from a published trial is not at the patient level, but it's still better than just taking the coordinate of a survival curve. That takes into account the at-risk data and the censoring data, and that's, you have 3.9 million cancer patients into that database of pseudo IPD. And that's what you're going to be applying your ML to, right?
Yeah, so exactly. And, this idea is still evolving. So I think what you just mentioned, Bruno, is, to me at least, it seems like like the core of everything. So we created one of the largest pseudo individual patient data sets out there, effectively having nearly 4 million data points that would correspond to 4 million individual patients. But these are pseudo patients, even though they are reconstructed in a way to be very similar to real patients. So that data set effectively had nearly 80,000, I think a little bit less than 80,000 trials worth of survival curves. So if we observe that just from the perspective of data science, like how much data could we use there to inform this machine learning model to be better, that seems like a very interesting opportunity. Now, I think, and I'm quite sure that by the end of this podcast, you will have another creative idea, Bruno, which is how do we combine these two, right? So in traditional machine learning, what we want is to have a number of inputs, and based on those inputs, we want to predict this survival curve. So I guess that's the first thing that's what we actually reasoned on our previous meeting brainstorm is what are these inputs? So these inputs could be how we describe the population, so key definitions of the population, maybe even some text, in just characteristics of the patients in that population. And especially, we want to focus on finding those inputs that have high predictive power of the survival curve that will contribute a lot to having that survival curve more accurate. So What are your thoughts on all that, Bruno? I know we discussed this previously, but I think it's interesting for everyone to hear.
So, in what I learned with you is that when we tackle a machine learning problem, the key is to define the problem very clearly in our mind. And sometimes that involves changing our mind a few times, as you know. But here, for me, the definition is to say we want to predict a survival curve, whether it's an overall survival or progression free survival. That's the output of an ML. The input of the machine learning is the definition of the population of that trial, probably vectorized as an embed, the definition of the treatment of that arm of the trial, probably defined as an embed. For example, the embed would have the value of taking into account the mechanism of action and the combination therapy of that arm. Of course, as an input, you also need the endpoint. Is it OS, PFS, or something else, something weird like EFS, EDS, etc. And of course, probably also the size of the trial. So that's the input of the machine learning. And then we would use some of the standard cat boost, XGBoost, random forest, and whatever the other ones are. And then the output of it ultimately is a KM curve, but there's something in the middle, right? Which is what we call the transitivity and a weighting of the different trial selectors. So maybe explain that middle part a bit more for the audience. How do we go from the population, the regimen, the endpoint, and the size of the trial? What's the missing part between that and a drawn KM curve, Kaplan-Meier curve, survival curve?
Yeah, so uh, I think there are probably multiple angles. And by the way, for everyone listening, this idea is evolving right now live, right? So what we are discussing right now at this moment, we haven't discussed much before. So we are virtually evolving the idea. Now,
It's
for
not built
me,
in public, it's to think in public. It's even the
yes,
next level. We're
th-
thinking
this
in
is
public.
this is virtually thinking in public. Now, the first thing that I'm thinking before just connecting to what you just said is that if we have 17,000 trials worth of data in reconstructed curves, we should probably, because right now we have those curves, right? We have the output, right? We have the output that we want to predict. Uh, Now we need to connect it to the input. So the input is this, what you were saying, like characteristics of the trial, as you said, maybe some text descriptions of the trial that we can then embed, and practically a lot of things that we have on Clean that are defined on Clean platform that describe the trial. Like, is it what is the state? What is the type of disease? What is the stage? What is the line of therapy? All those things that we can use to actually select that key population that we want. And if we can make a very large table and connect that table, and I think we can do that easy because every single one of those 70K trials that we created using the PoolZ project, it's actually created based on those specific trials. So we can easily relate them by the trial ID, right? So I think that's maybe the first step, probably building this huge data set. And then uh, the idea that comes to my mind is how do we actually enrich this? How do we add a step in between so that the machine learning model will not only depend on machine learning, it will also have this statistical feature in a way, so that it kind of uses both. It uses a little bit of machine learning, a little bit of statistics to combine them together into a good product. Now uh, we could use that weighting that you mentioned before and say, well, if I want to create a survival curve for EGFR mutated uh, lung cancer, I will just create weights for all the trials that we can pull. And if it's very similar to the definition of population that I'm looking for, then it's going to have bigger weight. If it's not similar, it's going to have smaller weights. So I could use a large number of trials, weight them, and then combine all that into one pooled curve. And that pooled curve could be an alternative way. So the way number one could be, hey, this is machine learning, this is a prediction. The way number two is this weighted approach. So we combine the two and we see how much they agree, disagree, and we can kind of use them to inform each other, to borrow information from each other. What do you think?
I like it. And in closing, I'd like to ask Eva to summarize what we said. So let's see what Eva ChatGPT, is it ChatGPT 5.6 or which one? It's
Yeah, I
actually the
think,
conversational, so
yeah,
I don't know if I have the full power of Eva here.
they rolled out the new one. I think 5.4.
5.4,
Yeah,
5.4. Yeah, yeah. Okay. So, Eva, I'd like to describe for you an idea called PoppyZ that I'm working on with Darko here. I'm going to describe it, and I'd like you to summarize it, number one, and then tell me whether two choice, whether it's genius or whether it's stupid. You only have these two choices. Okay. So let me describe what it is. So this is an idea at the intersection between machine learning and biostatistics, and it's a way to predict the result of clinical trials in cancer, in particular, predicting a survival curve, a KM curve, using pseudo IPD, pooled analysis, and machine learning. So the way PoppyZ works is that you feed PoppyZ with a definition of a trial that it has not seen, so it cannot cheat, right? And the machine learning algorithm is expected to predict the KM curve. And the way it does that is that it selects a list of trials that are the most relevant to this prediction, and it pulls it using our database of pseudo IPD. It pulls it and it weights the pooling of these trials based on probably two things. Well, the similarity of population, the similarity of regimen, of course, also the kind of endpoint, and also the N, maybe even the date of the trial. So first, summarize this in two sentences, and then just tell me the verdict. And please don't be too nice. I don't want. I'm here to learn the truth. I don't need you to tell me how smart we are. So tell me whether it's stupid. You only have two choices, and I want you to be very honest with us: stupid or genius.
All right, here's the summary. PoppyZ uses machine learning to predict survival curves for cancer trials by selecting and weighting a pool of relevant past trials based on population, regimen, endpoint, and other factors from a pseudo individual patient database to form a prediction. Now, my verdict? It's genius. Predicting KM curves from pooled weighted trial data is an ambitious and innovative approach.
I love you. Right.
I guess that's it. You know,
That's a wrap for today. So
yeah.
maybe we should not publish it. Everybody's copy us. No,
Just
no, no, no.
delete this podcast,
That is
please.
the podcast. All right, all right, no. We don't delete anything. And if you're listening and you also agree with Eva and you say that is genius, you have my permission and Darko's permission to compete with us and put more resources on us, compete with us, and make a ton of money out of it. Because what matters is not the idea; it's the execution. But we're gonna give you a run for your money. All right. So that's PoppyZ, and we'll talk more about PoppyZ later on. Darko, any final words before we close the podcast?
I'm nearly left speechless. You know, I think Ava told us it's a genius idea. I'm unbelievable, and I'm so happy that we can proceed with the idea, and hope we can develop it even more.
All
Maybe
right.
over the next podcast.
And Poppy is not there to say hello today because we want to know.
Poppy's actually there, but she's sleeping.
Oh,
When
we
she
don't want.
wakes up,
No, we don't want
I'm
to.
gonna tell her. I'm gonna tell her
Yeah, we
everything.
don't want to wake up Poppy when she's sleeping. All right. Well, thank you very much, Darko. Au revoir.
Au revoir.